Hey ladies, so today we're looking at section 7.3. We are going to be solving exponential equations. And this is going to be quite a bit of a review of what we did in Pre-Calculus 20, and we'll be applying some of the information that we learned in previous chapters, and we'll be applying it to help solve exponential equations. So just as a quick recall, we can rewrite exponential functions or expressions so that way they have the same base. If you guys remember how to do that, if we were given just 3, that is, we can rewrite that as 3 to the power of 1, or vice versa. Here, if we're given 9, we can rewrite that as 3 squared. So we're looking at here, we have that same base, that's your c value. So just write that as your c value to an exponent. In our third one here, we have 27, that is equal to 3 cubed. And 9 squared, we can rewrite this 9 term here as 3 squared. And then because 9 here was squared, we'll have that square on the outside of the brackets. And then we can rewrite that there as 3 to the power of 4. Alright? So, an exponential equation is an equation that has a variable in an exponent. Okay, so I'll repeat that. So, an exponential equation is an equation that has a variable in an exponent. So in this section, we're going to look at 2 different types of exponential equations. So our first one will be when we have common bases. So that makes life a whole lot easier when we have common bases. But in number 2, life's not going to be so easy. We're going to be having to deal with equations that don't have common bases. So we're going to look at some strategies about how to go about solving that. Okay. So we're going to look at the first type of exponential equations. So here we have common bases. And we can kind of split this up into 2 sort of, I guess, situations. So the first one is when we have an equation that begins with terms on both sides of the equal sign. So we have some on our left and the right. So as long as those are common bases, all we have to do is look at the exponents. So let's do an example here. So suppose we had 11 to the power of 2x minus 6, and that is equal to 11 squared. So notice here we have the same basis here. So all we have to do is look at those exponents. Okay, so we'll say 2x minus 6 must be equal to 2. Then solving for x, we're going to add 6 to both sides. Then what we have is 2x is equal to 8. And then to get x by itself, you're going to divide each side by 2. And what we're left with is x is equal to 4. Okay, so in those cases when we have the exact same base, all we have to do is look at those exponents. And another situation that we could have is, say, even looking at above, here we had to manipulate each of these, I guess, expressions that we were given to have the same base. So that's exactly what's going to happen. So for this one, we could have, or we will have terms on both sides of the equal sign. They may not look equal, but we can rewrite them to have the same base, and then we'll use the same process as we did in 1, where we're just looking at just the exponents, okay? So an example here is that we have, this is an example, so say we have 9 to the power of x plus 3 is equal to 81 to the power of 2x plus 9, just for example. So we want to have these in the same base. We have 9 and 81, so if you notice, 81 is 9 squared. So we'll rewrite 9 to the power of x plus 3. And we're going to rewrite 81 as 9 squared. That'll be in brackets there. And now we'll have the exponent on the outside of 2x plus 9 there. Okay, so we just rewrote 81 as 9 squared. And now we can apply, we're going to simplify our right hand side there. So we have 9x plus 3. That is equal to 9, and when we're dealing with this sort of situation, make sure you distribute that 2 to both places. So we're going to have 4x plus 18. So now that we have the same base, now we're just going to look at just the exponents. So we'll set x plus 3 equal to 4x plus 18. Right, so I'm just going to write this all the way up here. Alright, so now we're going to solve for x. Now get your x on one side, your numbers on the other side. So what we'll do first here is I'm going to subtract negative 4 on each side, or negative 4x, sorry. So we have negative 3x plus 3 is equal to 18. Then I'm going to subtract 3 on each side. So we have negative 3x is equal to 15. Then we're going to divide each side by negative 3. We want to get x by itself. And we have that x is equal to negative 5. Okay? So actually, if you put that back in there, you should find that those, your left side and your right side should be equal. So plug in x equals to negative 5 in for x into both of those, your left hand side and your right hand side. Make sure you're doing the original equations that I would give you, because in case you made an error over here, this will help to make sure that you can check your work, make sure it's right, before maybe there was any errors that could have been made. So, okay. So now let's move on to our second situation. So what happens when we don't have a common base? Yikes. What are we going to do? So our first option is we can use systematic trial, or what we know as trial and error. So for example, what if we had 7 is equal to 1.4x? Now there's no way that we could rewrite that, or at least that I can think off the top of my head, where x will make that true. So so what you're going to do is you're just going to try values and see where that goes. So for example, let's see what happens when x is equal to, let's say 5. I don't know what that'll give you, but let's try it out. So when we put in 1.4 to the power of 5, put that into your calculators, and you guys should find that we have 5.378, and that's rounding, of course. Alright, so we're getting close to 7, and we're still a little bit under, so we need to make this number a little bit bigger. So let's try what happens when x is equal to 6. We have 1.4 to the power of 6, and that there is equal to 7.530. You guys put that into your calculator. So what this basically is going to tell you is that, our x value, to make that true, it's going to be somewhere in between 5 and 6. And if you guys wanted to, we can go into 1 decimal point. So where would you want to start with? So we can even start with x is equal to, let's say 5.5. I won't ask you to go into more than 1 decimal. If you guys go to 0.1 of a decimal, that will be, I would say that'd be pretty good. So try putting 1.4 to the power of 5.5 into your calculators and see what you get. And what you should get there is 6.36. So we can still go probably a little bit closer. So let's try what happens when x is equal to 5.7. So you're going to put 1.4 to the power of 5.7. Put that into your calculators and see what you guys get. And that you should get about 6.807. So even then we can probably still get a little bit closer, but I'm not sure how much closer we can get. So let's try. Let's see what happens when we get 5.8 when we put that in for x. So let's try 1.4 to the power of 5.8 and see what you guys get. Put that one into your calculator. So we're trying to get as close to 7 as we can, but sometimes that's not always possible. So let's see what we get when we have 1.4 to the power of 5.8. And that there you should get 7.040. So looking at that, we're going to compare 5.7 and 5.8. It's only 0.04 off from when we have x is equal to 5.8. So roughly we could say that x is approximately equal to 5.8. And it's not exact. It's probably going to be a bunch of decimals. But, just play around, use trial and error, and see where you think that it could work, okay? So now that we've tried trial and error, another way that we could try solving is through graphing, and we've already done this with a different unit actually. So you guys remember when we were solving, say trigonometric equations, so there we had variables on both sides. So say we had sine squared of x is equal to cos squared of x. There's 2 different options that we could have done, and to solve by graphing. And so what we would do is you would graph each of them independently. So for this example, we're going to look again at 1.4 to the power of x is equal to 7. So what you would do is you're going to graph each side independently. So you'd have y is equal to 1.4 4x. Then your second graph would be y is equal to 7. And then from there, you're going to see where are those intersecting points. And actually, what we have here is, I was wonderful enough to give you those graphs. So look where those graphs intersect. And here, this value here is at x is equal to 5.78. So that's pretty close. We had 5.8 as our approximation. And I'm sure here that this is even itself is rounding as a decimal. So you guys have that option of graphing. Use your graphing calculators. Graph them both individually. Then you can look for those intersecting points. And then if you guys remember from back from those previous units, what we could have also done was we could move everything to one side and then look for where your value is equal to 0. So if we had 1.4 to the power of x is equal to 7, move everything to one side, so we'll subtract both sides by 7. So we'd have 1.4 to the power of x minus 7 is equal to 0. Graph this, or you'd graph it as y is equal to 1.4 to the power of x minus 7. Then look for where it's equal to 0. Okay, so where does it cross that x-axis? So both ways, no matter what you do, you'll get the exact same value. It'll just depend on where you're looking. So if you graph each of them independently, you'll look for where those two intersect. And when you move it all to one side, you'll look at where does it cross that x-axis, but you'll get the exact same answer. So you guys have already seen this before. We're just going to be looking at exponential functions instead of, say, the trigonometric equations like we did earlier. So now let's do some examples. The first examples here are that we need to rewrite each of each of the following values there as a base of 2. So we're kind of even going back to reviewing what we just talked about in the beginning of today's lesson. So first of all, we have 16 to the power of 3. How could we write 16 as a power of 2? And if you can't see it right away, you could always take this in small steps. Well, you know that 16 is equal to 4 squared. So what you could do is write 4 squared. So you have 4 squared to the power of 3. Remember to keep that exponent there if you have a 16 cubed. Then we could simplify that to be 4, and that'd be to the power of 2 times 3, which is 6. Then we can rewrite that as, we know that 4 is equal to 2 squared. And then go 2 squared, all to the power of 6. And then further simplify that to 2 to the power of 12. If you guys can see this without having to do all of this extra work, that is absolutely fine. But if you guys don't know where to start, if you can think of initially where it could be as a different square, that is absolutely fine. And then work your way backwards. Do small steps. If you can see it right away, that's awesome. If not, you know what? That's fine. Okay? So now let's look at, we have the cube root of 16. And if you guys remember this from Pre-Calculus 20, you should have learned that we can rewrite either cube roots or, say, radicals in general. We can write those as an exponent, and what you simply do is it's 1 divided by your index. That's that number sitting in that little area here that I have circled. Okay, so that's your index. So it's 1 divided by the index. And then from here, we're going to go through that same process, except this time we've already done that work. We already know what 16 is. So 16 is 2 to the power of 4. And that's all to the 1/3. Then using your exponent rules, you multiply, so you're at 2 to the power of 4 over 3. And one way you guys can check this is put this value into your calculator, then compare it by putting the cube root of 16. Those two values should be the exact same. So remember, we're just rewriting them. So that means that they are equal. So we're not changing the values, we're just rewriting them to look a little bit different, okay? So we're getting close to that 15-minute mark there, so let's change on over to video number 2.